Everybody, I hope you are doing well coming from a very long weekend. So for today, let me just give a discussion on a few more examples for our topic on propositions, truth tables, and our rules of replacement. Particularly, I would like to discuss the examples given in your modules. So please open now your modules on page 22. And if you're already in page 22 and browse it until page 23, you will find there 3 examples. So I will not review anymore the rules of replacement that we have discussed last time. So we have 14. So you're also familiar with the truth table. So going over now, example number 1. In example number 1, we are instructed to show that P, if and only if Q is equivalent to P and Q, or not P and not Q. In your module, this example was proven using the truth table. And since I know you're familiar with the truth table and you can easily follow the process of using the truth table, so I will not repeat the solution given there, but instead, let's tackle this problem using now the rules of replacement. Since you can already see that this is a logically equivalent proposition, then we can already proceed with the solution using the rules of replacement. And we can work with the left side, manipulate it to come up with the right side, or you can do it the other way around. You can work with the right side, manipulate it until you come up with the left side of the equation. So I'll just do one side. Maybe I can choose the left side, show that it is equivalent to the right side, and later on, I can give that as an exercise for you. You can work with the right side, show that it is equivalent with the left side. Okay, so if we will work with the left side of the equation, the first step that we can do is use our material equivalence. That's number 9 in your list. And using the material equivalence, P if and only if Q is equivalent to P implies Q and Q implies P. So we're working with the left side of the equation. So that's using material equivalence. Then after using material equivalence, comparing now your left side with the right side. In your right side, you don't find conditional statements. Rather, you find here your conjunction and your disjunction or. So that should tell us that we can actually convert first our conditional statements here to either conjunctions or disjunctions. And going over again your list, you can find there formula number 8, or the rule of replacement number 8, which is called the material implication. And according to the material implication rule, if you are given P implies Q is actually equivalent to not P or Q. And similarly, Q implies P using material implication is equivalent to not Q or P. Material implication. So this is equal to the right side, okay? Next, what else can we do now? So maybe what we can do is, let's compare again. Comparing the left side with the right side. For your right side, P and Q are together, not P and not Q are together. But if you will look at the left side, not P is with Q and not Q is with P. So it means we must find a way to put together P and Q, not P and not Q. And how can we do that? Look at this. We have here the disjunction. We have here a conjunction. We have here a disjunction. So maybe what we can do is to distribute each element here with the entire proposition here. So what rule is that? The distributivity rule. And if we will now do that, we now get not P, okay, and we use this, not Q or P, okay, or distributing now Q, we get Q and not Q or P, which should now be equal to the right side, and this is now using our distributivity rule. Then after using the distributivity rule, so we still did not get our goal to have not P and not Q together, P and Q together. Look at the resulting expression. We can again apply the distributivity law. And using the distributivity law again, so for this first expression, we get not P and not Q, which is one expression that we would like to have, or not P and P, okay, or we're now using that or there, distributing Q to each element there, we get Q and not Q, or Q and P. Again, that is using the distributivity law. Then after using the distributivity law, what did we come up here? So we already have what we desire, not P and not Q, Q and P, or P and Q together. So what's this? What's this expression here? Not P and P. Go now to formula number 13 under identity. In that list, you will find that not P and P. That's actually the in your list number 13, there are 8 items in number 13. That's the 7th, and this is equal to the false value 0. And similarly, this will be equivalent to the false value 0. So still under the identity, we now have one proposition or 0. That will now be the second under number 13. P or 0 is equivalent to P. So if you now count this as a single proposition, P or 0, then it must be equal to P. So this just leaves us not P and not Q. Okay. Or we have here 0 or a proposition again. So that should leave us Q and P, which is equivalent to the right side. So we just used here identity. We have again used identity here. And we're almost there. What's the right side of the equation again? We need P and Q, or not P and not Q. Not P and not Q is already here, or we just interchange the position. What property is that? By commutativity. So we use commutativity here. We use commutativity for the two. Then, let me write that first. So we have not P and not Q, or P and Q. So that's equivalent to the right side. What rule is this? Commutativity. Commutativity. Then again, using again commutativity, for this one, we interchange the two. We have not, or P and Q, or not P or not Q, which is already equivalent to the right side. Okay? Exactly equal now to the right side. So we have proven number one using two solutions. We have the truth table approach, which is given in your handouts, and we have our rules of replacement approach. Next, let's proceed with the second example. And in the second example, we are not required to prove that one side is equal to the other side, because if you will look at the expression there, number 2, what's the expression in number 2? We have P implies Q, or P implies R implies Q or R. We are not being asked to prove that this is logically equivalent to this one, because if that is the case, this must be a biconditional connective, or it's an equal sign, or in some cases three lines. But since this is an implication, so we are not going to prove that this is logically equivalent with Q or R. That's why the instruction there is to simplify. So let me just explain the steps given there. So we just want to make this expression simpler. So how can we do that? So if you will go over your handout, the first step given there is using material implication. Where is that step applied? For the first two expressions here, we can use material implication. P implies Q is equivalent to not P or Q. Okay, this is equivalent to not P or R. Then we use that connective. Don't forget the sign of grouping there. Implies Q or R. So that's the first step given there, material implication. And then the second step given there is by associativity. How do we apply associativity? Look at this. The connectives here are all the same. We have the disjunction or. So if we have the same connectives involved here, we can use the associativity rule. We can regroup the propositions here. The result will still be the same. And what can we regroup together? Since we find not P and not P here, then we can group not P and, or we can group not P or not P together. Or, ano yung natira? We have Q or R. Okay? Which implies Q or R. Next. Using idempotence for this one. Not P or not P must just be equivalent to not P. Diba? It's like you're asking the person you're courting, who do you like, me or me? Of course, me. You have no other choice, right? So not P or not P is just not P. So that should now leave us not P or Q or R. Implies Q or R. Next. The next step that you will find there is again using material implication. So where will we use the material implication there? Look at this. So we have our we have an implication here. So if we will apply the material implication rule, this entire thing here will serve as a single proposition. Since they are grouped together, we count this as a single proposition. So we are now looking at material implication, and the material implication rule states that P implies Q is equivalent to not P, or Q. Okay? You have P implies Q is not P or Q. And then, what can we do next? Here, this entire group is preceded by a negation. So we can use the De Morgan's rule. And using the De Morgan's rule, this will now become not P, double negation. That should be P. De Morgan's, we change the connective. So this now becomes P, and we also negate this, not Q or R, or Q or R. So just one correction before we proceed. I think in your notes or in the handout given to you, this grouping symbol is missing. Please just include it there. Next. What's next? By distributivity. So by distributivity, what will we distribute? And when do we apply distributivity? Earlier, we have applied associativity. Why? Because the connectives there are all the same. Now, compare the connectives here. We have the conjunction and we have the disjunction or. So, if that's the case, we can use distributive law. And if we now distribute this entire proposition here to each proposition inside this sign of grouping, what do we now get? We have P, okay, P, and then what do we use? Remember, we are distributing Q or R, so we now use this P or Q or R, and we have not Q or R or Q or R. So we distributed this one, diba? We have P or Q or R and not Q or R or Q or R. Distributive law. And then after using distributive law, you will find that we can apply here our identity. And what's the identity rule that can be applied here? We have P or not P is equivalent to the identity element or the truth value 1. P or not P, using the identity rule, this will give us the truth value 1. And then, since this is a single proposition and the truth value 1, using again an identity rule, P and 1 is just P. Using that identity rule, a single proposition, let's say proposition P and 1 is just equal to P. So that should now leave us P or Q or R. And that will now be the simplest form of the expression. Okay? So I hope you were able to follow that. And the last example given in page 23. So let's read the problem given there. On a rare TV game show, a young couple was shown 3 keys labeled A, B, and C, and was told that they could win a beautiful new home simply by picking the key, which opened its door. To help the couple make their decision, the MC of the show gave them the following pieces of information. First information, either key A will open the door or key B will not, and key C will. So that's the first. Second, if key B will not open the door, then key C will open the door. Third, it is impossible that either both keys A and B will open the door or both keys A and C will. Okay, so after a few minute reflection, the couple made the correct choice. Which key did the couple pick? Show a solution that uses a truth table. So actually, the answer is already in your module, but let's just explain it. So there are 3 possible keys to choose from. So either you choose key A, key B, and key C. Of course, if you're the contestant, if you choose key A, then you don't choose B and C. You can just choose one. Or if you choose B, then you cannot choose A or C. So similarly, if you choose key C, you cannot choose key A or key B. Next. So, to decide which to choose, good thing, the contestants enrolled in discrete math during their college days. And because of discrete math, they were able to win the house. Now, let's go back to the clues given by the MC. The first clue, let's read it carefully. Either key A will open the door or key B will not and key C will. So either, so ibig sabihin, pag sinabing either, you use the connective or, di ba? Either. So, it's either key A will open the door or ang sabi ron, key B will not and key C will. Key B will not, so we negate that, and key C will open the door. Next. Second condition. If key B will not open the door, then key C will. So, if key B will not open the door, then, so if then statement, If key B will not open the door, then it must be key C. So that must be the second clue. Third clue. It is impossible that either both keys A and B will open the door or both keys A and C will. So, again, it is impossible that either both keys A and B will open the door. Oh, let's stop there. It is impossible. So, A and B will not open the door. So, A and B will not open the door. Okay? So, it is impossible that either both keys A and B will open the door. Okay. So, we have to put the sign of grouping there. Okay. Again, read it. It is impossible that either keys A and B will open the door. So, this is for key A and B to open the door. And then the second part, or both, or. So, we now use or what's that? A and C. A and C. Okay. What's happening there? A and C. So, it is impossible that A and B will open the door or A and C will open the door. Okay, let's now proceed with our truth values. So, for the first clue that was given, not B and C. Not B and C. So, B is true. B is false. Not B will now become true. And C, so this will be false, right? False, and then or A. But A is true, so this must be true. Next, not B, this will become false, and C is also false, so this must still be false. A is false or false, so this must be false also. Next, not B. Not B, this will become true, and C is true. So, not B and C must be true, or A. A is false, but this is true, therefore this must also be true. So, there you have it for the truth values of the first condition. Second condition, not B implies C. Not B. This becomes true. This becomes true. This becomes false. If the first premise is false, this is true. This is true, we check the second. This is false. This becomes true because it's not B. Implies C. C is true. Therefore, this must be true. True implies true, true. And then for the last one, we have A and B. What's A and B? So that must be false. A and B is false. And then A and C is false. So false or false must be false. Not false must be true. Okay? Next. We have A or B. A or B is true. That's A and B pala. A and B, this will be false. A and B, false. A and C, false and false, will still be false. And then false or false would be false. And then not false must be true. Then the last one, A and B. A and B, false. A and C, false. False or false? False or false? False. Not false, must be true. Okay. So, how did the couple choose which key is the right key? They simply looked at the truth table. Based from the conditions given or based from the clues given, since for key C, all conditions were satisfied. All conditions became true. All clues are true for key C. Therefore, their conclusion is that, key C is the right key. And because of discrete math, the couple were able to win the brand new house. So see, discrete math became very useful for the contestants. So there you go, the solution of the 3 examples. So that ends that section. So next lecture video, I will be discussing arguments already. Then under arguments, you will find there the rules of inference, another set of rules that we will be using as we go along with the proving of arguments. Okay? So I'll be posting this in a while. And again, if there are questions, please feel free to email me. Please feel free to message me or just inform me. Okay? So there you have it. So see you again in the next lecture video.